Hi, this is Dr. Shulkat Sundar. In basic physics course in module 4 of light, we will discuss wave theory of light and interference of light. Objectives are to determine the intensity of superposed light waves. Number 1. Number 2. Conditions for constructive and destructive interference. Number 3. Intensity of interference fringes. What is light? Light enables us to see objects. The sun, a lighted candle, an electric bulb gives out the light. They are called luminous bodies. Now, this is light is coming from sun. Now, the basic question is whether light is a wave or particle. This is the nature of the wave. These are the particles. In the 17th century, two scientists had different views about the nature of light. Sir Isaac Newton proposed that light is particles. But Christian Highlands, he proposed no, light are waves. These are not particles. So wave or particles? In late 1600, Sir Isaac Newton believed that light travels in the form of particles which named as corpuscles. Then in 1678, Christian Huygens argued that light might be some sort of a wave motion. Huygens came up with Huygens principle that explained the light is a wave traveling through a medium called ether. Huygens deduced the laws of reflection and refraction and could explain double refraction to prove the theory of wave. However, if light behaves as waves, diffraction and interference should be seen using light. Wave or particles. Now, continuation of the previous slide, Huygens failed to provide any strong evidence to show that diffraction and interference of light occurred. Furthermore, couldn't explain why light has different colors at all. He didn't know that different colors of light have different wavelengths. Therefore, Newton's particle theory is acceptable since his strong evidence about particle nature of light. However, in 1801, Thomas Young's double slit experiment showed that light diffracts and produces an interference pattern. Therefore, Thomas Young successfully provide evidence that light has wave properties. He showed that light rays interfere with each other. Such behavior couldn't be explained by particles. Further, in 1860s, Maxwell developed a mathematical model of electromagnetism. He was able to show that these electromagnetic waves travel at the speed of light. Therefore, he asserted that light was a form of high frequency electromagnetic wave. In 1900, Max Planck was able to explain the spectrum of a black body radiator by assuming that light energy is quantized. That quantum of light energy was later named a photon. A few years later, in 1905, Albert Einstein used Planck's idea to explain the photoelectric effect to support the particle behavior of light and came out with a quantum theory. So first, Isaac Newton has given particle theory of light, then Christian Huygens wave theory of light. After Christian Huygens, Thomas Young given the wave theory of light using the Young's double slit experiment. Then came James Clerk Maxwell with the electromagnetic nature of light and emphasizing on the wave theory of light. Max Planck, to explain the black body radiation, he has given the particle theory of light. Sir Albert Einstein used the particle theory of light to explain the photoelectric effect, and ultimately Louis de Broglie stated that the wave particle duality of light, that means matter wave, light has both wavy nature as well as particle in nature. So this is known as the de Broglie's hypothesis. Now, wave particle duality. This is a double slit experiment. Here there are two slits. So a gun sprays bullets towards the target. This is the target. The resulting pattern is a map of the likelihood of a bullet landing at each point. Basically, these are the slits. Now the bullets are fired. Some of the bullets are firing on these walls, so they are not going out. So only these bullets are going out and they are producing this sort of fringes. This sort of pattern double slit experiment for waves. With waves, however, the result is very different because of interference. If a slit is opened one at a time, the pattern would resemble that for bullets, to distinct peaks. But when both slits are open, the waves pass through both slits at once and interfere with each other. If this slit is open, this slit is closed, then it will resemble the bullet type picture. But when the both slits are open, then they will interfere and produce this sort of fringes. Double slit experiment for electrons or photons. Now, the quantum paradox. Electrons, like bullets, strike the target at one time. This is a bullet striking the target at one time. Yet, like waves, they create interference pattern. Now, if they superimpose, then they will produce the interference pattern. If it is passing through this on the electrons, then we will get the first picture. This on this. Now, if they're like waves, then they create interference pattern. They produce the second picture. Here. Double slit experiment for light wave particle duality. If each electron passes individually through one slit, with what does it interfere? Although each electron arrives at the target at a single place and time, it seems that each has passed through. Thus, electron is understood in terms of wave particle duality or quantum mechanical theories. This is like this. So this is the electrons producing the waves passing through, they are interfering each other. That's passing through this slit and passing through this slit. They are interfering each other, so they are producing the fringes. So this is the wave particle duality. So light is a wave or a particle. Now just see this picture. So light is telling, or light is asking, am I an X-ray photon or a radio photon or a visible? Oh hell, why worry about all that again? I am not even sure if I am a wave or a particle. That is the photon's self-identity problems. On macroscopic scales, we can treat a large number of photons as a wave. When dealing with subatomic phenomenon, we are often dealing with a single photon or a few. As a conclusion, the scientists have observed that light energy can behave either like a wave as it moves through space, or it can behave like a discrete particle, or discrete particles with a discrete amount of energy, that is quantum, that can be absorbed and emitted. When light traveling through space, they act like waves. When light interacts with atoms or molecules, they act like a stream of energy called photons or quanta. Therefore, there are two theories of light which explain the nature of light. One is wave theory, which states that light as wave. Another one is particle theory, or second theory is particle theory, which states that light as a particle or photon. So theory of light, there are two. One is particle theory, another one is wave theory. So both these two within a whole is known as quantum mechanics theory or wave particle duality. So these are the photos of this great scientist Christian Huygens, Thomas Young, James Clerk Maxwell. Christian Huygens supported, his theory supported the reflection and refraction, Thomas Young, his famous experiment, Young's double slit experiment, which can explain diffraction interference, and James Clerk Maxwell, given few equations for electromagnetic theory of light, that is electromagnetism. Now, wave theory, or wave as the nature of light. Wave theory explains that wave as the nature of light. In wave theory, light is considered as an electromagnetic wave. This electromagnetic wave consists two components, which are electric field E and magnetic field H, which oscillate and perpendicular to each other, as well as to the direction of wave propagation as shown in figure. This is the figure. So this is an electromagnetic wave. It has two components, and both these components are perpendicular to each other. One is electric field component, another one is magnetic field component. Here in our picture, the pink one is electric field component and the blue one is the magnetic field components. And in between these two crests and two turfs is known as the wavelength. Distance between two crests, continuous two crests is known as wavelength, and this is the direction of propagation of light. According to wave theory proposed by Christian Huygens, light is considered to be emitted as a series of waves or wavefront in all directions. A wavelength a wave has a wavelength lambda, a frequency f, and velocity v. So this is the nature of, this is a wave. Here this is crest. So to consecutive separation between the two consecutive crests is known as wavelength. Similarly, separation between consecutive trough is also known as the wavelength. So this is the trough, this is also trough. So in between these two is also the wavelength. So one cycle means this is starting from this one crest, then trough, then again crest. So starting from this point to this point, this is the one cycle. And the time taken, this is one cycle. Time taken is what? It's time period. Time taken to move from this point to this point is the time period. Therefore, following properties can be defined for light by considering the wave nature in the figure shown here, or the waveform is shown. This is the amplitude. This is crest, this is amplitude. This is torque, is also amplitude. This is amplitude. Properties of light waves. Number one, wavelength, lambda. It is denoted by lambda. Wavelength is the length that one cycle or distance between two crests. This is the crest, this is crest, this is crest. So distance between two crests, this is the wavelength. Its unit is in meter. Number two, frequency f. How often cycle or cycle of wave repeats in 1 second? How often cycle of wave repeats in 1 second, or number of cycles per second? Its unit is hertz and represented by Hz. So this form, this is starting from this point to again producing crest, trough, then again crest. So from in 1 second, how many times this form is generated is known as the frequency. That means how many times this cycle is generated. So this is also known as cycles per second. Frequency is also cycles per second. Velocity. The velocity is represented by v. The distance covered by the wave in 1 second. Its unit is meter per second. So suppose this wave, it is covering a distance from this point to this point. So this is in 1 second. So this is known as the velocity. Number 4 is period or time period, represented by T. The duration of one cycle. It is reciprocal of frequency. Its unit is second, commonly represented by S. So T, time period T is equal to 1 by F, where F is the frequency. Wave number. It is represented by nu bar, the number of waves spread in a length of 1 meter. It is reciprocal of wavelength and its unit is meter inverse. So nu bar is equal to 1 by lambda. Nu bar is the representation of the wave number. Number 6, amplitude, and it is represented by A. The distance from the midline to the peak of wave. Amplitude is a measure of the intensity or brightness of light radiation. Here this is the amplitude. From this midline, it is moving to this distance. This is the amplitude. So distance from the midline to the peak of wave. So it is a measure, amplitude is a measure of the intensity. Actually, intensity is directly proportional to the square of the amplitude. So amplitude is a measure of the intensity or brightness of light radiation.